So to start this unit, what we want to do is go back and think about kind of our the scenario we've been in. So let me jump ahead to another slide here. And so throughout the semester, I've been going back to this picture where we've got some sort of a population, a large population, and within that population, there's some parameters that live there, like maybe mu, where mu is the actual average for the population, or pi, where pi is the proportion of something, proportion of females, or proportion of people who pass an exam, or something like that. And typically this population is difficult to access, it's large, something like that. And so what we do is we take a sample from the population, and within the population, or I'm sorry, within the sample we can calculate a statistic, like x bar is the average for the sample, p is the proportion of something for the sample, s is the standard deviation for the sample. So we've got all these statistics we could calculate, and the idea in statistics, in a course such as this, is how can we best estimate these parameters? Because these parameters, we're never going to know the value of those parameters, but how can we estimate them? And so going back to this slide, this is really the question for the second half of the course. It says, if we want to know something about the population, how can we estimate that? The ones that we're going to be looking at are means, standard deviations, proportions. Those are the main ones we're going to be looking at. Okay, so to estimate parameters, we're going to look at three different methods. One of the methods we've already looked at. One way to estimate parameters is with what's called a point estimate. And a point estimate is the easiest, and it is just exactly what it sounds like. You just say, okay, well, if I want to estimate mu, where mu is the actual average of that population, well, maybe I could just use x bar and say, okay, well, that's my estimate of it. And that's what we've talked about previously. It's like if we wanted to estimate proportions, well, you say, all right, well, there's this pi over here in the population, which is the actual proportion. Well, maybe what I could do is just use the proportion for my sample. That's p. So that's point estimation. This unit, we're going to talk about confidence intervals, which is another method for estimating parameters. And I'm just going to briefly, this unit, mention hypothesis testing, but that's really Unit 4. So Unit 3 is confidence intervals, Unit 4 is hypothesis tests. Okay? So a little bit more detail on, see that? Yeah. So a little bit more detail on point estimates. As I mentioned a moment ago, point estimates is, this is something we've talked about or kind of hinted at before. A point estimate is just a single value. It's the statistic, really. It's just a single value, a single statistic that's used to estimate some parameter. So we say, okay, well, we want to estimate mu, let's use x bar. We want to estimate pi, let's use p. We want to estimate sigma, maybe let's use s. That kind of idea. An advantage, really easy to calculate, right? You guys have done this. We've done this already. We did this in Unit 1. It's really, really, really easy to calculate a point estimate. The bad news is maybe it doesn't really give us that much information, right? Like if somebody has a really big sample, did a really good job sampling, used stratification and all these other really complicated ideas, and has a really big sample, and they come out with a point estimate, and then somebody else samples 4 people, and they get a point estimate. We'd like to think the one that had the really complicated, elaborate, big sample probably is going to give us a better idea about what the parameter is, right? We'd like to think that. But the point estimate doesn't reflect it, does it? No. So a point estimate, it's good because it's easy to calculate. but it's bad because it doesn't really pass on that much information to us. So it's lacking in a certain sense. What I always tell people is a point estimate by itself is meaningless isn't the right word, but it almost is meaningless. If somebody just says, here's what we think the average is, and that's all I give you, that's not enough. Okay? You can't make decisions based on a point estimate. So that brings us to confidence intervals. And a confidence interval takes, I think, a really intuitive approach to estimating parameters. So what we do with a confidence interval is instead of giving a single value, like saying, okay, well, we think mu is 5. Instead of doing that, we give you a range of values. We say, okay, well, we think mu is somewhere between 4 and 6. Right? It's an interval. We think the parameter is between here and here. An advantage is you can actually reflect how much information you have. Right? So, like, your information is how big your sample is, what you think the standard deviation. You can reflect those kind of things, because if you're not sure if you don't have that much information about the parameter, maybe you could reflect that by having a really wide confidence interval. You say, okay, well, we don't really know, so we kind of have to make our confidence interval wider to reflect that fact. Whereas if you have a lot of information about some particular parameter, maybe you could have a lot narrower confidence interval. So a narrow confidence interval means you've got a lot of information about it, and a wide confidence interval means, well, we don't really know that much about it. So that's an advantage. Another good thing is that a confidence interval actually has a chance of being right. A point estimate is almost never right, right? Right? Like if we're interested in the average height of Casper College students for some reason, okay, what would we have to do to get the actual true average height for Casper College students? Well, we'd have to somehow, some way, get how many people go to school at Casper College? Like 4,000 something. So you'd have to somehow measure the height for every one of those 4,000 some odd students, which would be a pretty difficult task, right? So somebody says, okay, well, let's just take a sample. So somehow we get a simple random sample of, I don't know, like 100 or 50 or 25 or some number that's determined somehow. We'll talk about that later. But say we get a sample of 50 Casper College students. Do you really think the average for those 50 is going to be exactly the same as the average for all 4,000? The answer is almost undoubtedly no, right? So the point estimate's not going to be right. But if we somehow did a confidence interval, could the confidence interval actually be right? Yeah, we could say it's somewhere between, we think the average height for Casper College students is somewhere between 5'6" and 5'11", or something like that. Is there a chance that could actually be true? Sure. So confidence intervals are a much improved way of doing estimation of point estimates. Next unit, we'll talk about hypothesis tests. And hypothesis testing, you guys have actually seen a hypothesis test before, maybe one or two of them, right? Didn't we talk about a normality test in Unit 1? That was actually a hypothesis test. I think we did another one, although I can't remember off the top of my head which one it was. So we've actually done a little bit with hypothesis tests, and we'll do a lot more for that down the road. Okay, so in most textbooks, when they start at this point, what they'll do is they'll say, okay, we want to do a confidence interval for mu. We want to do a confidence interval for the true average. So you can put yourself in the situation of like wanting to say, well, we want to know what the actual height of Casper College students is. We want to know what the true average height for Casper College students is. We don't want to do a point estimate because Brooke told us those are bad by themselves. What we want to do is a confidence interval. So we're in the situation, we want to know what mu is, but we're going to assume one thing here. We're going to assume that we know sigma. What does sigma stand for? That's the standard deviation for the population. In reality, do you think people usually know what sigma is? The answer is, of no, they don't. But at this point, we're going to assume that we do. We're going to assume that we know what sigma is. All right, so what I'm going to put on this next slide is, it looks kind of messy. It's really not that bad. And you guys should be able to kind of follow step by step what's going on. I'm not going to ask you to do this, but I think, at least for one of these, I think it's important that you guys see what's going on, because what this really does is it derives the formula. We're coming up with the formula for the confidence interval. All right, so what we do is we go line by line by line by line by line. And all we're going to do is make an argument of why we can go from this line to this line to this line to this line, and then what we're going to do is, at the very end, we're going to end up with the formula. And so just using a series of logical steps, we're going to end up where we want to be. So this first equation, 0.95 is equal to the probability that z is between negative 1.96 and positive 1.96. Where does that come from? What does that mean? What's going on there? How can I say that? Yeah, literally, all that is referring to is this z-table, right? We've been using these z-tables over the last, I don't know, week or two, something like that. All this is saying is, remember, z is a normal 0, 1, so it's already been standardized. So it's the chances that z is between negative 1.96 and positive 1.96 is 0.95. Do you guys remember we did an example in class where we had to find the middle 95% of the area on a z-curve? Do you guys remember that? And we came up with negative 1.96 and positive 1.96. And I said, oh, those numbers are going to show up again. And you guys looked at me like I was crazy. They do. This is where they show up. Okay? All right, so we've started with something we know is true. We know it's true because we looked it up in our z-table. Okay, so all I'm going to do is work with the right-hand side of this. So going from line 1 to line 2, all I've done is replace z with x bar minus mu divided by sigma over root n. Can I do that? Obviously I can, because I did. Under what maybe a better question is, under what circumstances can I do that?
When you know mu and you know your standard deviation.
And how many samples?
And you know the number of trials.
So I heard a couple different things there. But remember, I can do this if x bar is normal. If you have something that's normal, and you subtract its mean, divide by its standard deviation, you get a normal 0, 1. That's just standardizing, right? So in order to go from step 1 to step 2, I had to have known what? X bar was normal. If x bar is not normal, you can't do this. Okay? And so consequently, you're saying, well, then why are we going to go along with this if we don't know that that's happening? What happens when you do these confidence intervals and hypothesis tests and so forth? There's a set of assumptions that for each one that you have to verify. So what we're going to have to do in order to be able to use this formula that we're deriving, we have to know that x bar is normal. If we can say, oh, x bar is normal, then we're good. Okay? Now, x bar being normal, remember that was the very last theorem we talked about last unit. That was the central limit theorem, wasn't it? Remember, x bar to be normal, either the population had to have been normal, or what? A large sample. Remember that I did that little demonstration on the, yeah. So that's what's going on there. And then once you get to this point, that's really all there is to it. At this point, it's just a little bit of algebra, right? So I'm dividing by something, so I multiply by sigma over root n to all three parts. And then I get rid of the x bar by subtracting it. And then I divide by -1, which means I have to flip all the inequality signs. And then to get here, I just kind of flipped it back in the way that people normally see the inequality signs. And so what you see here is the chances that mu is between this and this is 0.95. So this and this are what are known as a 95% confidence interval. We're 95% confident that mu is between here and here. Does that kind of make sense? And the nice thing is, we can calculate this and this using what we know, right? If you take a sample, won't you know what x bar is? Sure, you can just average the values and that's x bar. 1.96. Well, that's just a number. N, if you take a sample, won't you know what N is? Yes. The only thing that you may not know is sigma, but what did we assume on that previous slide? We assumed that we knew what sigma is. Now later on you're saying, well, we're never going to know what sigma is, and that's probably true. So later on we're going to be able to change this so we can, we can change it if we don't know sigma. Let me ask you this. What would happen, do you think, if we wanted to do a confidence interval that was not 95%, like we're going to do 99% or 90? What would change? Yeah, that's right. The negative 1.96 and the positive 1.96. If you wanted to do a 99% confidence interval or a 90% confidence interval or whatever, all you have to do is just change these numbers here, right? And the other thing that I'll point out is this. I've got x bar minus something, x bar plus something, and it's the same something. So sometimes you'll see people write this like this. Yeah, it's the same thing. This is just a little bit more concise way of writing this and this endpoint. So when you see the plus or minus, it just means you have to add and subtract that thing. Does that make sense? Now, next slide says, what did we have to know? And that's what I talked about a moment ago. We assumed to go from, I think it was like line 1 to line 2, from the first to the second, we had to know that the distribution of x bar was normal. And remember, thinking about when we talked about the central limit theorem, that could happen in one of two ways. One, either we know somehow that the population is normal, or two, the sample size is large. So if you've got a really big sample size, it doesn't really matter. We can kind of rely on the central limit theorem. If we have a small sample size, then we have to know the population's normal. And remember, in Unit 1, didn't we do assessing normality? Like we did QQ plots and all that kind of stuff that helped us be able to make those kind of decisions. So we're going to go back and rely on that.
You said larger than 30, right, for the sample size?
Usually textbooks, for some reason, had this arbitrary cutoff of n bigger than 30. I don't know to what degree we'll end up using that, but for some reason that's kind of a magical cutoff. It's not really magic though, you know, like for some populations they might be so skewed that you need it much bigger than 30, and for some they might be fine if it's less than 30. Okay, so let's stop here and then we'll do some examples.